NSF was measured by calculating the probability measured in percentage of switching a response following the presentation of misleading negative feedback, no reward, which occurs in a low proportion of trials. Thus, NFS was high if participants switched response following negative misleading feedback, lose shift behavior, and low if participants maintained the usually rewarded option following negative misleading feedback, lose stay behavior. See Figure 1 for an illustration of the PRL task. Control measures, mood, and double-blinding efficacy. Transient changes in mood state have been demonstrated to influence cognitive functioning. Federmeyer et al. 2001. And of particular relevance to this research, probabilistic learning. Beckett et al. 2014. Therefore, we checked for the potential mood effects induced by tryptophan intake on PRL by administering a computerized adaptation of visual analog scale, VAS, which was programmed and run in PEBL, Mueller and Piper 2014, and has previously been used by our research group. Ong, Lai, Taik et al. 2016, Ridby et al. 2017. 7 dimensions of mood alertness were recorded with a total minimum score of 7, low mood alertness, and a maximum total score of 147, high mood alertness. The double-blinding efficacy of placebo tryptophan administration was checked by a questionnaire given to participants at the end of the experiment. Procedure. This was a double-blind, placebo-controlled, mixed design experiment. Participants were required to attend a session lasting approximately 70 minutes. After screening for eligibility, participants were instructed to refrain from eating and drinking for a minimum of 3 hours. They first signed a consent form, followed by the mood questionnaire, VAS time 1, and were then asked to complete 2 blocks of the PRL time 1. They were then randomly assigned to receive either tryptophan or placebo. 60 minutes following tryptophan intake, which corresponds to peak plasma concentration, Marcus et al. 2008, or placebo, the VAS and PRL were completed for a second time, VAS time 2, PRL time 2. Following this, participants filled out the tryptophan placebo double-blind questionnaire and were debriefed. Statistical analysis. Statistical analysis were performed using SPSS version 23, SPSS Inc., Chicago, Illinois, USA. Sample size was chosen to deliver power at 0.8, an alpha level set at 0.05, and a large effect size D of 0.8. G times power 3.1.9.2, Germany. For all the dependent measures of the PRL, we first run an independent sample t-test at baseline, time 1, between placebo and tryptophan participants. If there was no significant performance difference at baseline, we calculated a percentage change at time 2 compared with time 1, and used these new values to compare placebo with tryptophan using another independent sample t-test. A full breakdown of the raw data is shown in Table 1. Mood data were analyzed using a two-way factorial repeated measures analysis of variance, ANOVA, where the factor of time had 2 levels, VAS 1-2, and drugs had 2, placebo and tryptophan. The double-blinding efficacy of tryptophan placebo was analyzed using a percentage correct measure. A score of 100 was given if a participant correctly identified condition, whereas a score of 0 if not. Results. PRL negative feedback sensitivity, NFS. To assess the impact of tryptophan administration on NFS, we first took a measurement at baseline prior to drug intake. There were no significant difference in NFS performance between placebo and tryptophan participants. T42 is equal to negative 1.38 and P is equal to 0.172. The D is equal to 0.41. Therefore, we calculated a change in performance expressed in percentage from time 2 after drug intake to time 1 before drug intake, as in time 2 over time 1. Here, whilst there was a reduction in NFS between time 1 and time 2 for placebo participants, tryptophan abolished this change. As a result, NFS was significantly higher for tryptophan than placebo participants. T at 42, T subscript 42 was equal to negative 2.80, p-value of 0.008, D is equal to 0.84. See figure 2a. In figure 2a, it states A, percentage change from baseline time 2 over time 1 for placebo and tryptophan participants with respect to NFS performance. NFS was significantly higher when comparing tryptophan to placebo participants. B, as for A, there was no significant difference. PRL reversal learning errors. The same analysis were applied for reversal learning errors. At baseline, there was no significant difference in performance between placebo and tryptophan participants. T is equal to 42. T at 40 subscript 42 is equal to negative 1.04, p-value of 0.301, and D is equal to 0.31. Both placebo and tryptophan participants improved from baseline. This change in performance from post-drug to pre-drug was not significantly different between the two groups. T subscript 42 equals negative 1.33, P is equal to 0.188, D is equal to 0.40. PRL total errors. As for NFS and reversal learning errors, there was no significant difference between placebo and tryptophan participants at baseline. T subscript 42 is equal to 0.34, p-value is 0.703, and D is equal to 0.11. Tryptophan also did not affect changes in performance from baseline. T subscript 42 is equal to 1.21. The p-value is 0.231 and D is equal to 0.36. See figure 2c. Changes in reversal errors are independent of changes in NFS. To confirm that NFS and reversal errors provide separate measures of performance, we run a bivariate correlation analysis between the variables reversal errors, measured as change in performance from pre-drug to post-drug, and NFS, also measured as a change in performance. There was no significant correlation between reversal errors and NFS. R is equal to 0.05, p-value is equal to 0.701. See figure 3. Control measures, mood and double-blinding efficacy. There was neither a significant main effect of time, F1 42 is equal to 1.04, p-value of 0.313 on mood scores, nor a main effect of drugs. F is equal to 1 at 42 is equal to 1.45, p-value of 0.234, nor a drugs times time interaction. F is equal to F subscript 142 is equal to 0.81, p-value of 0.373. The probability of participants guessing the correct drug, placebo or tryptophan, was about chance level, 56%. We report a selective effect of tryptophan supplementation on NFS, but not on PRL. Whereas for participants in the placebo group, their NFS decreased from pre-drug administration to post-drug due to a practice effect. Tryptophan suppressed this reduction. This had the net effect that NFS was higher for participants in the tryptophan condition than the placebo controls, i.e., when measured as a change in performance from baseline to post-drug administration. PRL, reversal errors, and total errors performance, however, was unaffected. Exploratory analysis confirm that reversal errors and NFS are dissociated from one another. The observation that reversal and total errors decreased for the tryptophan group from pre-drug to post-drug, but not NFS, did not, demonstrates that tryptophan did. This demonstrates that tryptophan did not affect the overall acquisition of the task, but inhibited NFS learning specifically. This finding is in line with the tryptophan depletion studies, Evers et al. 2005, Talbot et al. 2006, Finger et al. 2007, Van der Place and Feenstra 2008, and suggests that reducing or increasing serotonin in humans does not modulate reversal learning. Nevertheless, global serotonin 5-HT or prefrontal cortex depletion studies in animals and manipulations of serotonin postsynaptically by SSRI in both animals and humans demonstrate that serotonin can affect reversal learning. Clark et al. 2004, 2005, Chamberlain et al. 2006, Berry et al. 2010, Brown et al. 2012, as do studies that target 5-HT receptors. Blugaris et al. 2008 are finding that tryptophan supplementation increased NFS is similar to some reports in which small but not large doses of SSRI were administered. Chamberlain et al. 2006, Berry et al. 2010. Interestingly, our data support the idea of a disassociation between PRL and NFS performance as reported in depressed patients and those with serotonergic transporter polymorphisms. Murphy et al. 2003, Taylor Tavares et al. 2008, Den Ouden et al. 2013, supporting the view that the PRL is a broader measure of cognitive flexibility than NFS, which isolates sensitivity to negative feedback. To end this, ATD studies have highlighted a role for serotonin in aversive processing and punishment prediction. Cools et al. 2008, Robinson et al. 2012. In conclusion, our data provide preliminary evidence for a role of tryptophan supplementation on NFS, an effect that is independent of reversal learning. The current study adds to a complex picture in which general serotonergic activity manipulations, SERT, promoter polymorphisms, SSRI administration, and targeting F5HT receptors differentially affects NFS and PRL. Future studies that address the SSRI equivalent of the applied tryptophan dosage and its effect on 5-HT levels would be critical, taking into account respective non-linear effects. Although tryptophan supplementation on its own is not going to replace SSRI usage at the therapeutic level, finding out the optimum dosage may support cognitive performance with little to no side effects. Data availability. The datasets for this manuscript are not publicly available because data can be made available upon request. Requests to access the datasets should be directed to luca.aquili@shu.ac.uk. This name of the article is Dissociable Effects of Tryptophan Supplementation on Negative Feedback Sensitivity and Reversal Learning. This article comes from Frontier Behavioral Neuroscience, 2019, Volume 13, Issue 13, Volume 127. Frontier Behavioral Neuroscience, published in June 28th of 2019. The authors again are Martin Thurkel, Laura M. Barker, Thomas Gauher, Nazgul Nayeb, and Luca Aquili. This is from the Department of Psychology, Sociology, and Politics, Sheffield Hallam University, Sheffield, United Kingdom, and this was edited by Greg Stanwood at Florida State University in the United States. Thank you again for your time. This is Eric Michael Lloyd, Master's in Psychology neuropsychology concentration.